Hi, Mr. Sapone here, and today we're going to look at electron configurations, or where electrons live in an atom, and how to write configurations. The idea of planetary orbits is sort of commonplace, but it's completely incorrect. Electrons do not orbit the nucleus like planets. Electrons are actually going to exist in specific regions inside an atom, and it's probability based. There's no guarantee an electron will be here, but there are 4 orbital shapes called SPDF. We remember that by the saying you see on the top of the screen, students, please don't fart. These are your S orbitals. These 3 are your P orbitals. These are your D, and these are your F. And notice that there is 1 orbital, 3, 5, 7. A very easy pattern to remember. Each orbital will hold 2 electrons. So this one orbital will hold 2 total electrons. Each one of these orbitals holds 2 electrons, so there's 6 total electrons here, and these 5 will hold 10, and of course the F is going to hold 14. So that's where those numbers 2, 6, 10, and 14 come. And I know this looks very complicated. What are these shapes? Well, these regions, this region right here, there would be a 90% chance of finding the first 2 electrons in an atom in this 1s shell. And actually there could be larger versions of these orbitals. This is a 1s. You could have a 2s, which would just be a bigger version of itself. And there would be a 2p, which would be a bigger version of the 2p. And don't worry too much about that right now. We're going to see what these mean. Just realize these shapes, based on a whole bunch of math, wave equations, Schrodinger wave equations, and so on, these are where we find electrons in an atom. And these 4 shapes. And it's based on probability, only a 90% chance of finding an electron in these regions. But there's an S, a P, a D, and an F shell or orbital. So we kind of treat an atom like a building, as sort of an analogy to figure out where electrons are. We know that there's energy levels around the atom. This would be the nucleus in the center. All the protons and neutrons are in there. And we kind of put atoms in rings around the nucleus. And this is a good way to model where electrons are by energy levels, because each ring is a new energy level. But electrons aren't actually orbiting the atom like planets, so that's where this ring kind of falls through. Electrons are going to be in regions like these around the atom, where the middle of each one of these pictures would be a nucleus. So electrons are in very weird locations around an atom. But the first floor, think about it, this first floor is the first energy level, or the first ring. So this is energy level 1, energy level 2, energy level 3, energy level 4, energy level 5. Each energy level in an atom is like the floor of an apartment building. And in this first energy level, there's going to be an s orbital. And the second energy level, there's going to be an s and a p orbital. Think of them like apartments. This is going to be 1 apartment here. And on the second floor, there's going to be 2 apartments, an s apartment and a p apartment. Third floor is going to have an s, a p, and a d, 3 apartments. And the fourth and the fifth and so on would have 4 apartments. And on the first floor is going to live 2 electrons. There's 2 electrons living here, 1, 2. On the second floor, we could have 8 electrons living in these 2 apartments. 2 in the S and a big family of 6 in the P. On the third floor of any apartment or electron, there's going to be 18 total electrons. And then 32, 32, 32. So I understand this is a little confusing right now, but we're going to think of these energy levels as rings around the atom, though we know that electrons don't orbit the nucleus like planets. They exist in those weird regions, those weird shapes we saw on the previous screen. But each energy level is going to hold so many electrons. And we talked about a 2882 rule, and you're probably thinking, well, how does the third energy level hold 18 when we said it goes 2882? And we're going to see where that comes from in a slide or two. We're going to go through the full electron configuration setup. All right. So we're going to look at the Aufbau Principle, and that basically says that electrons are going to fill up an atom starting with lower energy to higher energy. So we're going to fill up the earlier rings most of the time first, the later rings after, but there's going to be a few deviations from this. So what we like to do is we write the numbers 1 through 7 down, and we write an S after them. So 1, 2, 3, 4, 5, 6, 7, and it's very important that you do this neat if you're doing this at home, and you'll see why in a second. Then we write the numbers 2 through 7 down and put a P after them. And we're starting to get a pattern here. Hopefully you see it. S, P, D, F. Students, please don't fart. And now we're going 3 through 7. And finally 4 through 7. And I know we probably don't know where this is going yet, but it'll become clear in a bit. These are the 4 electron orbitals, and we're drawing this sort of half triangle for a reason. Now we're going to draw arrows diagonally, starting with the 1s. Doom, doom, doom. That's why it's important that you draw this very accurately so you don't mess these arrows up. And what we're going to do at this point is we're simply going to follow the order of the arrows. And we have a 1s, right, first. Then we have the 2s, followed by 2p to 3s, followed by 3p, 4s, right? All this is done. What comes next? Well, the first part of it is a 3d, 4p, 5s, then the 4d, 5p, 6s. And what we're really going to do is we're going to take this order all the way through and we're going to write it down. We're going to follow that order. And you're going to end up with a very long order like this. And it's going to be very, very important to us. And the final thing what we're going to do is we have a 1s, a 2s, a 2p, a 3s, a 3p, and so on. After every s, we're going to put a 2 as a subscript. After every single s, we're going to put a 2 as a subscript. After every single p, we're going to put a 6. P, put a 6 here. So after every single s, you put a 2. After every single p, you put a 6. And of course, after every single d that you find on here, you're going to put a 10 and a 14 for an f. And you end up with this awesome list, which is your standard ground state electron configuration order. This is the order that electrons will fill up an atom in. The first 2 electrons are going to go in the 1s orbital. The second 2 go in the 2s. The next 6 electrons go in the 2p. The next 2 go in the 3s. The next 6 in the 3p. The next 2 in the 4s. Oddly enough, the next 10 go back in the 3rd energy level. So this is the order at which electrons will fill up an atom. And there's a few deviations to this on the periodic table. Copper is a notable example. There's a few minor cases, or not minor, but there's a few cases where this order is not followed for various reasons. But this order is going to be super important to us. This is going to be the order in which electrons are going to fill up an atom. And don't think of this as an equation. This is not a math equation. You're not squaring anything or cubing anything or multiplying anything. All this 1 right here signifies is the energy level. Energy level 1. Then we have the orbital shape. There's S, there's P, there's D, and there's F. So we have 4 orbital shapes. And this 2 over here only tells me the number of electrons that you have in that orbital shape. So you have an energy level, the shape, and the 2. Just like 5d10, you're not multiplying anything, you're not raising anything to the 10th power. This is just saying energy level 5, there's a D shape, and it holds up to 10 electrons. So this order right here that we got from that kind of sort of broken Aufbau triangle is going to be super important to us. We need that order. And what we're going to simply do is we're going to write electron configuration for a few atoms. So if we take aluminum, and what I did with this list right here was I simply cut out part of this list because we don't need the whole list, so I kind of just stopped it here. I cut it out and I drew it up top. Aluminum has 13 total electrons. So how would I write the electron configuration for aluminum? You can think of these orbitals or these shapes as containers that hold electrons. And it must be full. One container must be full before you fill the next one. So this S holds 2 electrons. So you have to put 2 of aluminum's 13 electrons in here before you start going into this shell. So each one of these is a container. They hold electrons. This holds 2, this holds 2, this holds 6. 2, 6, and so on, the whole list. The idea is the Aufbau principle is that you have to fill up the lower energy, the preceding containers, before you fill up the other ones. So the first 2 electrons are going to go in the 1s orbital, and I have 13 electrons down here for aluminum. So the first 2 go there. Of course, the second 2 are also going to go into the 2s. This is full now. It holds up to 2. It's full. This holds up to 2. It's full. The overflow we got to put in here. How many can we put in here? Well, it holds up to 6 electrons. So the next 6 go in there. And of course, the following 2 are going to go in here. And now there's only 1 left, but this is full, so we have to put the 1 in here. And how do we write this electron configuration out? Well, we are going to simply follow this order. We have a 1s2, we have a 2s2, we have a 2p6, we have a 3s2, and we have a 3p6. P1. Uno. This holds up to 6, but how many do I have in there? I only have 1. So I finish the last one as a 1. And that's how you write an electron configuration. You're just filling up this order and going forward. And we'll do another example to make sure we got it down. This would be the electron configuration of aluminum cleaned up. Remember, this P only has 1 electron in it, so we did not fill it up. It could hold up to 6 electrons, and we have to fill it before we go on, but it's not full, so we write it as 3p1. That's the electron configuration of aluminum. So let's look at oxygen. Oxygen, of course, has 8 electrons, 8 protons on a periodic table. We're just assuming it's neutral. So we have a neutral oxygen atom, 8 protons, 8 electrons. And these orbitals are containers. And we're simply going to fill the containers up with electrons. The first 2 go in the 1s. The next 2 go in the 2s. And now I can fit up to 6 electrons in here, but I don't have 6 electrons to put in here. I only have 4. So how do I write this electron configuration? Well, I'm going to go 1s2, 2s2, 2p4. There's only 4 electrons in there. And this is how we write electron configurations. Once it clicks, it's not a super hard thing. Why doesn't the 2882 rule work? Why does the third shell hold up to 18 electrons? Well, let's look at it. First, energy level 1. Energy level 1, we put how many electrons? 2 electrons. Energy level 2, how many electrons? 2 electrons. Energy level 2, we're still in energy level 2, we put 6 more. So energy level 2 can hold 8. So the first 2 electrons go in energy level 1, the next 8 go in energy level 2. And energy level 3, you're putting 2 in the S and 6 in the P. So of course the next 8 goes in energy level 2. And we had that 2882 rule. Where do the next 2 electrons go? Well, they go in the 4th energy level. And what about the next electrons? The next 10 electrons go back into the 3rd energy level. So you would actually put the next 10 in the 3rd energy level. So the 3rd energy level holds up to 18 electrons. So that's why we use the 2882 rule and why I said there was limitations to it. After you get to element number 20 or 20 electrons, the order changes due to various reasons. So this is the order that electrons will fill up an atom in. This is where the 2882 comes from, but this is the much more robust and more complicated form of it. Hopefully that helps you write electron configurations. This is Mr. Sapone.